Good afternoon, everyone. I'm very pleased to be here at CEFCO in Vilnius to present our recent work on optical key distribution with a noisy laser source, conducted in collaboration with Mikołaj Lasota from Nicolaus Copernicus University in Toruń, Marcin Jarzyna, Konrad Banaszek, and Rafał Demkowicz-Dobrzański from University of Warsaw. This work is part of my industrial doctorate at the University of Warsaw, conducted in collaboration with Quantum Optical Technologies company, and the program is supported by the Ministry of Science and Higher Education of Republic of Poland. In any communication system, two users, traditionally called Alice and Bob, wish to exchange information securely over a physical channel. However, this channel can be monitored by an eavesdropper, who may try to intercept or infer the exchange data from the physical signals themselves. There are several approaches to secure the optical communication. Quantum key distribution addresses the most powerful scenario, so an active eavesdropper who can interact with or modify the transmitted signals. QKD offers unconditional security, even against attackers with quantum capabilities, but it requires complex and expensive hardware. Another family of protocols assumes a passive eavesdropper, and these include wiretap channel models that provide security when the eavesdropper collects much less signal than the legitimate receiver Bob. In our work, we focus on optical key distribution, which also targets a passive eavesdropper, but under more challenging condition. It enables secure key generation when the eavesdropper collects much more optical power than the legitimate receiver. OKD uses macroscopic signals and simple practical setups to generate a secret key, and it makes it a lightweight alternative for QKD. To illustrate this attack scenario, please imagine a telescope transmitting optical signal to a ground-based telescope. Even if the eavesdropper has larger telescope and captures more of the optical power, the OKD protocol still ensures the secure key generation. In the OKD scheme, Alice uses a continuous wave laser to encode random bits, but by finely modulating the optical intensity between two levels. The optical signal is sent via a direct optical channel to Bob, and we assume that fractions of the signal tau b and tau e are received by Bob and Eve respectively. Detection outcomes create two Gaussian distributions with their variances determined by the detection noise. Since Eve receives more optical power, her distributions are more separated. However, the security of the protocol doesn't rely on secrecy, but on fundamental physical constraints, specifically the noise floor from the detection and the fact that outcomes from the detectors are not correlated. After the detection, Bob sets discrimination thresholds to assign outcomes to bits, zeros and ones, and outcomes falling in between them are simply discarded. In order to generate the final secret key, Alice and Bob need to do some post-processing steps. It is key reconciliation, error correction, and privacy amplification. We can quantify the security of the protocol using the eavesdropper's advantage parameter. It's defined as the ratio of tau e to tau b, which represent fractions of the signal, multiplied by the ratio of sigma b to sigma e, which represent the detection noises. Okay, binary modulation with hard decoding is only one example of OKD model. It's straightforward to implement, but not the only option. We can compare it with two other approaches. Firstly, the Gaussian modulation, which is known to maximize the information rate in classical communication. And secondly, with soft decoding, where all measurement outcomes are retained for key generation rather than being discretized. When we look at the formulas for these three cases, we see an interesting pattern. Gaussian modulation with soft decoding is only dependent on the eavesdropper's advantage parameter. Binary modulation with soft decoding introduces another parameter to optimize, the modulation depth. And finally, binary modulation with hard decoding adds yet another variable to optimize, the position of the discrimination thresholds, kappa. Okay, but what happens to the OKD protocol when a noisy laser source is introduced with Gaussian noise sigma s? Here we focus on the binary modulation, so Alice is finely modulating her optical intensity between two levels, as in the first example, but now these levels include some additional noise. The optical signal is still split between two receivers, Bob and Eve. However, now both Bob's and Eve's detection outcomes have higher overall noise, and this effect is captured by a relative source noise contribution. It's defined as the amount of signal received by Bob, tau b, multiplied by the ratio of source noise to Bob's detection noise. It is very important to include a noisy laser source in the security analysis because it introduces correlations between Bob and Eve that weren't present before. These correlations are unfavorable because they reduce statistical independence between Bob's and Eve's detection outcomes. As a result, Eve gains more information about the transmitted signal. It is visible from the joint distributions. Um, Correlations are visible on the joint distributions, indicating as you can see, the histograms appear more elliptic, not circular as in the uncorrelated case, and it indicates that there is a shared noise that leaks key related information. Okay, in this part of the work, we compare three OKD models, optimizing the secret key rate for each case over all available parameters, so the modulation depth and position of the discrimination thresholds. This plot will show the secret key rate in bits per slot as the function of eavesdropper's advantage, expressed in decibels. The solid line corresponds to Gaussian modulation with soft decoding, and for non-zero source noise, it drops to zero sharply. Dashed line corresponds to binary modulation with soft decoding, and it consistently stays lower than that of Gaussian modulation. The dot dashed line corresponds to binary modulation with hard decoding, and it becomes particularly interesting when source noise is high. Then it outperforms both Gaussian modulation and soft decoding, achieving a non-zero secret key rate even in the regions where the others fail. This behavior becomes more clear when we examine 2D histograms of the detection outcomes. Let's now focus on the binary modulation with hard decoding and with the parameter value SB equal to 0.05, so the red dot dashed line on this plot. When eavesdropper's advantage is 0 decibels, then there are almost no correlations between users, and histograms appear circular. When eavesdropper's advantage increases, Eve receives more optical power than Bob, so Eve's modulation depth exceeds Bob's. But we are able to keep the discrimination thresholds close together. When eavesdropper's advantage increases further, then strong correlations develop between Bob and Eve. In this case, soft decoding fails to generate any secret key, but hard decoding succeeds by adapting the discrimination thresholds and forcing them further apart. Okay, the two OKD models differ in the way their parameters are optimized. In the soft decoding case, there is only one parameter to optimize, the modulation depth. This plot shows its optimal values. As you can see, it stabilizes at a constant value. And it means that we can't improve the performance of the protocol further using this model alone. On the other hand, hard decoding have two parameters to optimize, so modulation depth and position of the discrimination thresholds, and both these parameters increase sharply at a certain point. They allow to achieve non-zero secret key rate in the narrow region, which is often referred to as the waterfall region. Okay, the optical key distribution with a noisy laser source has already been implemented in an experimental setup, which showed the secure key generation with the presence of an eavesdropper. This setup achieved a key generation at a maximum distance of about 80 kilometers with a rate of about 1 megabit per second. In this experiment, the transmitter exhibited a realistic level of noise, what significantly reduced the secret key rate, because when the transmitter would be optimal, so there wouldn't be any source noise, then the secret key rate could have been up to 10 times higher. However, crucially, if the OKD protocol had ignored the source noise, it would not have remained fully secure against an eavesdropper. With that, I would like to conclude my presentation. Optical key distribution enables secure key generation with simple macroscopic signals. Laser noise creates correlations that must be included in the security analysis. Soft decoding fails when correlations are high, but hard decoding can still extract bits by adapting thresholds, and the experiments show secure key generation at 1 megabit per second over 80 kilometers. With that, I would like to thank you for your attention.
And now we have time for questions. I should ask, but I am not expert on quantum cryptography, so I cannot. So please, somebody else. Okay, if it is not the case, so thank the speaker again.
Thank you.